Hey everyone, so this is the very last thing that we need to talk about with simple harmonic motion, and it's something called the wave equation. Now, one of the really nice things about the simple harmonic motion that we've been talking about so far is that it can actually be represented by a mathematical equation. What do I mean by that? We can basically come up with an equation in order to predict where the object is going to be at every moment in time based off of certain variables. So let's if we want to come up with an equation that represents simple harmonic motion, we need something that is repetitive. Because remember, when we're talking about something like mass on a spring or a pendulum, the object always returns back to the same points in a very set amount of time. So we need an equation that also always repeats itself and returns back to those same positions. For example, a line is not repetitive. It changes. Once we go through a certain point, we never return back to that point. Parabola also is not repetitive. You go too far away, it only maybe returns to certain points once or twice, but then never any more than that. So what equations would be periodic? Well, the trig functions. If you recall in math, trig functions are repetitive. They go back and forth, and they oscillate back between 2 points over and over until the end of time, essentially. So what we can do is have displacement, velocity, and acceleration represented by either sines or cosines as a way of coming up with this wave equation. Now, the way we kind of come up with the equation, this wave equation is we want to consider a scenario. So we're actually going to consider the case where we have a block attached to a spring. We have the block kind of pulled down, stretched, elongated, and then when we release it, we know that it's going to oscillate back and forth. Now, we might ask ourselves, what type of graph would this position versus time look like? Well, we know that if we start it at its stretched position, we're starting at its amplitude. So of these two trig functions, sine and cosine, only one of them starts at the amplitude, cosine. So it should end up looking like this, a cosine graph, going from its negative amplitude or positive, depending on what direction we're pulling it, but that's not the point here. The point here is that it's going to start at an amplitude, and then it's going to go up and back down to that original amplitude, and it's going to do that within its defined period. So what we can say is that the position graph should look like this: a cosine blah 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 t. A because that's the amplitude, and that's kind of what the coefficient in front of a trig function represents. It represents the amplitudes that it reaches. Because remember, sine and cosine, when you graph those always oscillate between 1 and -1. So if we had it a times cosine, it's going to oscillate between a and negative a. Now, I don't really know what's inside this cosine part. I just know that it's going to vary with respect to t. So this is what my equation is going to look like so far. All right. Now, the actual equation for a position is going to look like this. And this actually is on the reference table. X of t, so the position as a function of time, is going to be represented by the amplitude times cosine of 2 pi ft, f representing the frequency. Now, this is going to be true for any simple harmonic motion. However, I do want to point out is that depending on the scenario, that cosine might be changed to a sine. All right. There are scenarios where instead of having it start at its amplitude, it could start at the equilibrium position where it actually is zero position, and then it goes to its amplitudes. Like for example, if you had a pendulum and you whack the pendulum uh, at the moment right after the whack, it's still at the bottom of its swing. It's still at the equilibrium position, so x would be zero. But then it would start kind of going in that the periodic motion. So in that scenario, it would actually be better to put sine in there. So just be aware that the trig term, the sine or cosine, could be swapped for these equations depending on the scenario, but the form of the equation always stays the same. It's always going to be a times the trig function, and inside the trig function is going to be 2 pi ft. Right? And this is what the graph is going to end up looking like as we kind of have it oscillate back and forth. So it's going to, again, be at one of these amplitudes. It doesn't matter. In this case, we're going to start at the positive amplitude, and it's going to oscillate one time every period. So 2 times after 2 periods, and so on and so on. Now, what about the velocity? Well, we can kind of consider that same scenario. So again, if we brought this object, we stretched the spring so it's at its positive amplitude, and we released it, we know that it starts with zero velocity, right? Because we're just bringing it to that point and then releasing it. So that means that we should be looking for a trig function that starts at zero and then goes over to its max and min points. So of those graphs, the velocity would be represented more like a sine curve, and it would end up looking something more like this. The reason it goes down, it really depends on the scenario, but the idea is that if you pulled the object to the positive amplitude, pulled it to the right, then the velocity should be pointed negative. So that's why it would go like this, right? One thing to keep in mind is that the period also stays the same. All right, so that is one major thing to keep in mind about all these wave equations is that the period is constant throughout. And again, same thing for the acceleration. Again, we know that when we're at the amplitudes, the acceleration's at their maximum values, and then they go to zero. And again, because the acceleration and force go in the same direction, if I pull it to the positive amplitude, the acceleration should be pulling me in the negative direction. So it should look exactly like the position graph, but negative cosine instead of positive cosine. All right. So there is another way to figure out and verify that this is actually true, and you can take derivatives. I only say this because some people are deciding to take the APC, but also a lot of you are taking calculus or pre-calc, so you probably know about derivatives and integrals a bit at least. So if you actually take the equation for position and you take the derivative of it, you would end up getting essentially these equations. So the position graph would end up looking something like this: negative a 2 pi f sine 2 pi f t, with this term just being simplified as Vmax. And then if we did it again for acceleration, um, basically the sine turns into cosine, and we end up getting that. So again, we end up getting the whole, you know, positive cosine for our position, negative sine for velocity, and negative cosine for the acceleration. And again, in all three cases, it's always the maximum term times some trig function with 2 pi ft. So that's why I was saying before is that understanding the form of the equation just is useful. You don't need to memorize it specifically because again, scenarios change. Maybe instead of it starting at its positive amplitude, it might start at its negative amplitude. In which case, all these equations would have like an additional, or would be negated. Um, it might start at a equilibrium position and might go positive, it might go negative. So there's so many different variations of these graphs. What matters though is that it's that the equations will always be amplitude times trig function of 2 pi ft. And like I said, you don't need to actually do derivatives. I just showed this because I know a lot of people do like derivatives, and that's they're a lot their go-to once they learn how to do it, and it makes life a lot easier. But like I said, you can figure out what the equation is supposed to look like, whether it's sine or cosine, by just using conceptual understanding. Like again, where is it going? Where is it? Is that positive or negative? That's basically it. So this is kind of what I was saying before, that the period, the frequency, all those numbers stay the same, regardless of which of the motion graphs we're talking about. However, one thing to keep in mind is that their maximums, their amplitudes, are not the same, right? While they have the same shape, one being cosine, one sine, the other one negative cosine, uh, and while they may complete one full cycle in the same amount of time, their amplitudes will be different. Now, this is actually really important because there are questions on the AP where they might give you one type of motion graph and then they'll ask you to draw the other one. So they might give you a velocity graph and then ask you to find the acceleration. And the key thing to keep in mind is knowing, you can look at the velocity graph and know exactly what your period is supposed to be. You can look at the velocity graph and think to yourself, and figure out, when is the acceleration hitting its max and min points, all these things, and you could figure that out from the velocity graph. So, um, just keep that in mind. So these are what all the graphs look like. And again, notice how they all complete one full cycle in the same amount of time. These periods are all the same terms, but the sizes can vary. Sometimes one might be bigger, one might be smaller. Right. So here's the first question. Pause the video. We're self. We'll go over a second. Alright, so we want to draw the position versus time graph for an object oscillating with some period. Now they don't tell me where it starts at, so I can have it start wherever I want, right? It could have started at amplitude, it could have started at the equilibrium position. It really doesn't matter. So I'm actually going to start it at the equilibrium position. It says that it has a period of 6 seconds. So as you recall, one thing that I like to do is I like to make points. I like to figure out where the points are before I start connecting the dots. So I know it's going to start here. If it has a period of 6 seconds, that means the ending for my graph should be here. And because of the way that this is going to be, it's going to be a sine curve. The It crosses that equilibrium position a second time halfway. So at 3 seconds, it's going to pass there as well. I also know that it's going to hit a maximum halfway between these 2 points, and halfway between these 2 points is going to hit a minimum. So I can connect the dots, and boom, there I have my position graph for the 6 seconds. Now, in the other case, where the object has twice the frequency, if I think back, what does that mean to have twice the frequency? It means it has half the period. So if I have the object starting at the same point, then the graph should end up here. So this is where the end of my full cycle should be. Halfway is where it's going to cross the equilibrium position again. The amplitudes should be somewhere halfway between these 2 points and halfway between these 2 points. The amplitude should still be the same. So I end up having this as the second graph. And if we actually extended this for one more cycle, we'd see that we'd actually get two waves in that same amount of time. So that's why this would be twice the frequency. We see it twice as often as we would see the other graph. All right. Here's another question. Pause the video work self. I'm going to go over in a second. All right. So they want to know which one has the greatest frequency, which one has the greatest period. So looking at this, greatest frequency is the one that we see the most often. The purple one is the one we see most often. So this one has the greatest frequency. And the one that has the greatest period is the one that's the longest or the less frequent, red. All right. And that's basically it. So if you have any questions, feel free to let me know. Otherwise, good luck and have a great day.